Did you know you probably have comet dust in your hair right now? Tiny cosmic grains drift through our skies every single day, and the gold in your ring was forged in the violent collision of dead stars. Out there, planets can swap places, and it can literally rain diamonds. The universe is stranger and more beautiful than we imagine. Today, 15 discoveries that might change how you see everything. Astronomy has transformed how we see our place in the cosmos, from early stargazers with simple tools, to listening across invisible wavelengths, to observatories above the blur of our atmosphere, and James Webb a million miles out, revealing the first galaxies. We are living in a golden age of discovery, ready to explore the weird, the wonderful, and the truly mind-blowing? Buckle up. Let's get started. 15 awe-inspiring astronomy discoveries. Nailed it? Like, subscribe, share your coolest cosmic trivia in the comments. Every single day, Earth gets a cosmic dusting, about 14 tons of tiny grains, bits of rock metal from comets from asteroids. These particles, called micrometeorites, are so small you'd need a microscope to see them clearly. Beat. Most are thinner than a human hair, but they settle everywhere. On your clothes, your car, even in your hair. Right now, you might be carrying a piece of a comet that's been wandering the solar system for millions of years. Watch how it happens. As a comet approaches the sun, heat frees dust from its icy surface. Jets of vapor puff away like tiny geysers, pushing grains into a glowing halo and a trailing tail. Those particles drift through space, forming vast streams. Beat. Some eventually cross Earth's path, patient travelers on orbits that intersect our sky. When they enter our atmosphere, they heat up and glow. Most too small to make shooting stars you can see, but still countless specks reach the ground. What's left cools into minuscule beads and flakes that float down like invisible snow. Here's something wild. Scientists estimate that over 5,000 tons of this cosmic dust falls on Earth every year. That's enough to fill a small swimming pool. Beat. Most of it comes from comets, icy wanderers that release dust as they warm near the sun. Some comes from asteroids colliding in space, grinding rock into fine fragments that spread along their orbits. How do we know? Researchers collect micrometeorites from remote snowfields, deserts, and even rooftops, then study their chemistry and structure under powerful microscopes. Iron, nickel, tiny crystals, cosmic fingerprints. Under magnification, they're beautiful. Dark, glassy spheres with smooth fusion crusts. Beat. Speckled textures like constellations frozen in stone. Beat. Some show delicate radial patterns where molten rock once spun in mid-air. You can picture the journey written on their surfaces. Outgassed from a comet. Beat. Sunbaked. Beat. Air-scorched. Beat. Earth-cooled. There's a sweet paradox here. Most micrometeorites are fragile, yet they survive a fall at tens of thousands of kilometers per hour by being small enough to shed heat quickly, and they carry stories, traces of early solar system minerals. Beat. Tiny bubbles of once molten glass. Beat. Even hints of organic compounds, cooked but not erased by their fiery descent. Little known fact. You can actually hunt for micrometeorites at home. Start simple. Beat. After a good rain, check your roof gutters, place a clean tray, flat pan in an open area. Let any water evaporate, then gently sift the residue. Use a small magnet. Many micrometeorites are rich in iron and will stick. Sweep slowly. Patience is key. Safety tip: wear gloves if you're digging through debris and avoid magnets near sensitive electronics. Beat. Keep your tools clean to reduce contamination. Under a microscope or a strong jeweler's loupe, look for tiny glassy or metallic spheres with smooth, fusion-crusted surfaces. They're often dark gray to black, sometimes with a subtle sheen. Size matters. Beat. Most genuine micrometeorites are about the width of a grain of sand, up to a millimeter at most. Too big, and it's likely industrial slag or welding spatter. Shape helps too. Perfect or near-perfect spheres, sometimes with delicate dimples or a frosted texture. Beat. Many show a thin, shiny crust and lighter interior where they've chipped. Not everything magnetic is cosmic. To rule out Earth-made lookalikes, scan for symmetry, smooth glazing, and that telltale fusion crust. Beat. If it's jagged, porous, or flaky metal, it's probably terrestrial. For a cleaner hunt, try smooth concrete after rain, a balcony tray, or even fresh snow in winter. Let it melt through a coffee filter, then inspect what's left with your magnet and lens. And if you do find a candidate, store it in a tiny labeled vial. Beat. A personal meteorite museum in a bottle. Meanwhile, scientists are doing the same at scale, sifting Antarctic snow, Arctic ice, and desert sands. In labs, they slice micrometeorites thin as a hair to analyze their minerals grain by grain. They can tell comet dust from asteroid dust by chemistry and texture. Beat. Comet grains often show more glassy, volatile-rich material. Asteroidal fragments tend to be rockier, with crystalline metals. Put it all together, and a planet-wide picture emerges. Dust streams tied to famous meteor showers. Background grains from ancient collisions. Seasonal pulses as Earth plows through debris trails. Even weather plays a part. Gentle winds drift particles onto rooftops. Rain washes them into gutters. Calm nights let dust settle on cars and windowsills. Quiet deliveries from space. Think about the scale. Beat. From the vacuum of space to the tip of a hair, a journey measured not just in kilometers, but in time. Many grains predate Earth's oceans, and yet they land here, on sidewalks, beat, gardens, beat, city streets, folding the vast into the familiar. Beat. That's the magic of cosmic dust. Even if you don't find one, the search connects you to a bigger story. How dust from ancient comets and shattered asteroids becomes part of our world. We breathe the same air they glow through. We walk the ground they gild. So the next time you brush your hair, think about this. You're carrying a tiny piece of the cosmos. A reminder that Earth is just one small part of a much bigger story. And that bigger story is falling softly all around us. Look closely. The universe leaves clues. When you think of stars, you probably picture blazing balls of fire like our sun, hot enough to vaporize anything nearby. But not all stars are scorching. Beat. Meet brown dwarfs, stars that never quite made it to stardom. They're not massive enough to sustain nuclear fusion like real stars. Beat. And among them, Y-type brown dwarfs are so cold, their surface temperature is barely warmer than a summer day, around 80 degrees, about 27 degrees C. In theory, you could touch one without burning your hand. Soft whoosh. Here's the twist. A Y-dwarf isn't a solid rock you can stand on. It's a dense, gas giant-like world, layered with, beat, hydrogen, helium, laced with exotic clouds. Beat. Think of it as a failed star that feels more like a super Jupiter, cool enough to hold in a thermal image. Beat. Too faint to see with your eyes. Trivia. These chilly stars were first confirmed in 2011 by NASA's WISE telescope. WISE scanned the sky in infrared, where warm things glow even when they look invisible in normal light. Beat. That's how we found them. Flecks of heat against the dark. Soft whoosh. Some Y-dwarfs are even colder than Earth's Arctic regions, with temperatures dipping below freezing. Imagine a star colder than a winter night. Beat. It defies the picture in your head. No roaring furnace, just a dim ember, barely warming the space around it. Little known fact, Y-dwarfs are so dim, they're nearly invisible to most telescopes. They emit mostly infrared light, so we needed advanced tech to find them. Cryogenically cooled detectors. Long exposures. Careful sky maps. Beat. And even now, some might be floating undetected in our cosmic backyard, closer than the nearest proper star, Proxima Centauri. If they are, they're hiding in the wavelengths our eyes can't see. Scale check. Our sun's surface blazes near 5,500 degrees. A Y dwarf lounges a few dozen degrees above room temperature. Beat? Same universe, same physics, wildly different outcomes. Soft whoosh. What would one be like up close? No sharp surface, just thicker, denser air as you dive. Gravity tugging stronger than any planet you've known. Beat. Clouds of water. Ammonia could swirl in muted bands. Storms churning slowly in the infrared glow. The light would feel strange. No bright glare, just a soft warmth you don't see, but instruments do. Scientists read these worlds by their spectra. Tiny fingerprints of molecules etched into their light. Beat. Methane. Water vapor. Ammonia. The colder they are, the richer the chemistry we can tease out. Beat. Each dip in the spectrum tells you about pressure, temperature, clouds stacked layer by layer. Beat. Think of a Y dwarf next to a steaming cup of tea. The cup shimmers with heat wisps you can see. The dwarf barely glows at all. Beat. Yet in infrared, the picture flips. The dwarf pops bright. The cup fades. Soft whoosh. More perspective, brown dwarfs bridge the gap between stars and planets. They form like stars, collapsing out of cloud, but they live like planets, cooling with time, darkening with time. Beat. The youngest can start warm and ruddy. The oldest fade toward the temperature of a spring day. Beat. Cosmic adolescence that never quite becomes adulthood. Why does it matter? Because extremes test our ideas. Beat. Why dwarfs tell us where star ends and planet begins. They refine how we hunt exoplanets, infrared techniques, chemistry signatures, delicate light curves. Beat. And they remind us our neighborhood is not empty, just quieter than we thought. Imagine a map of the nearby stars. Bright names we know, and between them, question marks. Places where a faint, cool wanderer could be drifting, unnoticed. Beat. Not because it isn't there, because we weren't looking the right way. So, while our sun burns hot and loud, these cosmic underachievers keep a low profile. Cool enough to hold in your mind like a secret. Beat. A star you could touch, at least in temperature. Is the universe's way of keeping us guessing. Soft whoosh. And if the idea feels impossible, that's the point. Beat. The cosmos makes room for fire, frost, furnaces, embers, stars that roar, stars that whisper. Look closely. Even the quiet ones shine. From stars that whisper to worlds that might answer. Here's the hopeful part. Beat. Earth might not be rare, not even close. Soft whoosh. Thanks to NASA's Kepler and Gaia, we've learned a stunning truth. As many as 1 in 6 stars could host an Earth-sized planet in the habitable zone. Beat. The Goldilocks band where liquid water can persist. Not too hot, not too cold. Beat. Do the math across the Milky Way, and you get a number that feels impossible. 10 billion. Beat. 10 billion Earth-like worlds, scattered through spiral arms and star fields. 10 billion places where clouds might gather over oceans, where rain might fall. Beat. Kepler did the heavy lifting first, staring at dense star fields, measuring tiny dips in light as planets crossed their stars. Beat. A blink in brightness, repeated on schedule. That's a planet. Before retiring in 2018, Kepler confirmed over 2,600 worlds. Beat. Thousands more remain candidates, hidden in the noise, waiting for patient eyes. Soft whoosh. Then Gaia stepped in with the big map. Over 1 billion stars measured in exquisite detail. Positions, motions, distances that sharpen our statistics. Beat. Gaia helps us know how common planets should be, star by star, region by region. Beat. Here's the headline you came for. About 20% of sun-like stars might cradle a planet just right for life. Not guaranteed Earths, but cousins. Beat. Close enough for hope. Soft whoosh. Zoom out, and the diversity is dazzling. Super Earths. Rocky giants with thicker air and stronger gravity. Mini Neptunes. Small gas worlds with hazy skies and deep weather. Water worlds. Global oceans without continents, where tides and chemistry write alien stories. Beat. Some look familiar. Kepler 452b is nicknamed Earth's cousin. About 60% larger than our world, circling a star much like the Sun. Beat. Its year is close to ours. Its daylight would feel recognizable, not a twin, but a neighbor you might wave to across the fence of light years. Soft whoosh. Remember, our methods are picky. We find big planets easier than small ones, close in orbits easier than wide ones. Beat. So if we're already seeing thousands, imagine how many hide just beyond our current reach. Planets that don't transit. Signals drowned in stellar noise. Beat. They're there. We're getting better at listening. Soft whoosh. What makes a world truly Earth-like? Right size helps. Right temperature helps. Beat. But composition matters. Rock underfoot, an atmosphere that breathes, a magnetic field to shield. Beat. Plate tectonics to recycle minerals, a stable star that doesn't tantrum. Time. Billions of years for chemistry to get clever. Beat. Even so, liquid water is the great filter. Find the water and you narrow the search. Beat. That's why the habitable zone matters. Not a promise of life, a permission slip for possibility. Soft whoosh. With 10 billion chances, the question tilts. It's less if life exists, and more where and how soon we'll find it. Beat. Maybe it's microbial mats under an alien sun. Maybe it's forests breathing a chemistry we'll recognize by the colors of reflected light. Maybe it's something we haven't imagined. A living ocean whispering through storms. Beat. We're building the tools. Infrared eyes to read atmospheres for water vapor, methane, oxygen. Spectra like fingerprints, tiny dips and wiggles that betray clouds, pressure, and chemistry. Beat. The same trick we use on brown dwarfs, now aimed at worlds that might host seas and skies. Soft whoosh. Every detection sharpens the map. Kepler taught us the crowd is big. Gaia tells us where to look next. Beat. TESS sweeps wide, finding nearby candidates bright enough for follow-up. And the newest observatories read starlight with surgical precision, pulling planets out of glare like fireflies from noon. Beat. Consider the odds. There are more stars in our galaxy than grains of sand on many beaches. If even 1 in 6 holds a temperate, Earth-sized world, then the night sky isn't just pretty, it's populated. Beat. Some of these worlds will be older than Earth, with head starts measured in eons. Some will be younger, still cooling, still settling. Beat. Some circle quiet, steady suns. Others orbit red dwarfs that flare and test their atmospheres with bursts of light. Variety isn't a bug. It's the universe's favorite feature. Soft whoosh. Why does this matter? Because the idea of 10 billion Earth-likes reframes our place. We're not a fluke. We're part of a pattern. Beat. A pattern that says life's ingredients show up often under many skies, on many shores we can't yet see. Beat. One day, we'll confirm a blue world close enough to study in detail. We'll read its air like a book. We'll watch clouds move. We'll measure seasons. Beat. And maybe, just maybe, we'll spot chemistry that doesn't balance without biology. Soft whoosh. Until then, we keep counting. We keep listening. We keep widening the search. Beat. Because when the galaxy holds 10 billion maybes, you don't need certainty to feel wonder. You just need to look up and do the math. Beat. 10 billion potential Earths. 10 billion invitations. 10 billion reasons to believe we're early in the story, not alone in it. And somewhere out there, a coastline is catching its first sunrise. Soft whoosh. We'll find it. It's only a matter of time. Soft whoosh. Meanwhile, closer to home, Saturn. A masterpiece of geometry circles a giant. Saturn's rings stretch over 140,000 kilometers, wider than Earth. Beat. And yet, their thickness, only a few hundred meters, razor thin on a planetary scale. Imagine a Blu-ray disc scaled to Saturn, a kilometer wide, a millimeter thick. Beat. Seen edge-on at equinox, the rings almost disappear, light skimming knife edges of ice. What are we looking at? Trillions of pieces, mostly clean water ice, dusted with darker grains. From powder-fine snow to house-sized boulders, with rare chunks bigger still. They keep their poise because physics is patient. Beat. Countless gentle bumps shave away up and down motion until a flat sheet remains. Resonances ripple that sheet like music, waves traveling through ice and shadow. Take the grand tour. Soft whoosh, the bright B ring, the delicate C ring inside it. Closer to the planet, a faint D ring glows, easy to miss unless you know where to look. Outside, the A ring gleams, split by the Cassini division, a grand gap carved by orbital rhythms. Within the A ring, the Encke gap, a narrow lane where tiny pan plows, raising waves along the edges. Daphne skims another gap, sculpting scalloped walls that curl like lace. Beat. Now the F ring, narrow, wild, braided. Shepherd moons Prometheus and Pandora tug its strands, teasing clumps into knots and streamers. Hidden moonlets leave propellers, double-lobed wakes where gravity paddles the ice. Sometimes the rings grow spokes, mysterious radial shadows and bright streaks that glide across the B ring. Electrified dust, magnetism, sunlight, nature sketching with charged powder. That's the delicacy we're talking about. They're built from trillions of icy fragments. Beat, from powder-fine grains to mountain-sized chunks, all orbiting in a flat, disciplined plane. Knife-edge lighting reveals topography measured in meters across thousands of kilometers. Stand back, and the rings are grandeur. Step close, and they are snow. Beat. Why so thin? Gravity and collisions. Countless gentle bumps shave away vertical motion, while resonances from moons conduct waves that march across the rings, settling particles into an exquisitely level sheet of ice and shadow. How did such finery arrive? One idea. An icy moon wandered inside the Roche limit, where tides forbid a body from holding together. Torn apart, its pieces spread into rings. Beat. Another. A comet or moon shattered in a catastrophic impact, seeding ice that collisions then refined. Here's the twist. These rings might be temporary. Evidence hints they brightened within the last 100 million years, when dinosaurs still walked Earth, and they could dim over roughly the next 100 million. Micrometeoroid dust slowly darkens the ice. Saturn's magnetic field and upper atmosphere sip away material. A steady ring rain falling into the planet. Tiny ice grains and charged water molecules spiral inward, feeding auroras and airglow. A slow leak, a fading fountain. Beat. Cassini weighed in, literally. During its grand finale, it dove between Saturn and the rings, skimming the plane and sampling nanograins. Those measurements mapped ring mass, traced ring rain, and sharpened debates about age and origin. Put it together, and you see a living system, shaped by tides, tuned by resonances, thinned by time. Shepherd moons. Prometheus Pandora patrol the edges, carving gaps, corralling ripples, keeping order in that impossible thinness. Up close, the rings glitter. Sunlight casts knife-edge shadows that betray their geometry, vast in width, delicate in depth. So the next time you see Saturn, remember, those grand arcs are fragile, a fleeting sculpture of ice and physics, glowing for a cosmic moment. Look closely. Even giants can be gossamer. Soft whoosh. Soft whoosh. From knife-edge ice to cosmic forges. Every gold ring, silver coin, platinum necklace, beat has a larger origin story. These precious metals weren't born on Earth. They were forged in the violent collisions of neutron stars, the ultra-dense cores of dead stars. Beat. Picture two city-sized suns, side by side, each with more mass than our sun packed into a sphere the size of a town. A teaspoon of neutron star would weigh a mountain. Beat. They orbit, spiral inward, space-time itself ripples, magnetic fields arc like iron rainbows, and then impact. Beat. Inside that flash, something extraordinary. Our process nucleosynthesis. Atoms swallow neutrons faster than they can decay, sprinting up the periodic table in seconds. Beat. Gold, silver, platinum, uranium. Beat. A new light blooms, a kilonova. Early, it shines blue. Lighter, our process material. Beat. Then it reddens as lanthanides thicken the glow. The wreckage becomes an expanding shell of treasure dust. Beat. 2017 made it real. GW 170817. Gravitational waves chirped through LIGO and Virgo. Beat. Telescopes swung worldwide. In optical and infrared, they watched the afterglow rich with heavy elements. Sound and light from a single cosmic event. Proof that these collisions are gold factories. Beat. How much? A merger can forge more than an Earth's mass of heavy elements in one blast. Beat. With gold and platinum that dwarf everything humans have ever mined. Most of it sails into space, dusting galaxies with future jewelry. Beat. Follow the journey. Soft whoosh. Ejecta cools into tiny grains. They drift into star-forming clouds, mixing with gas and ice. Beat. In protoplanetary disks, those grains get locked into pebbles, rocks, worlds. Beat. On one small planet, a rare vein forms. We dig it up and call it precious. Beat. There's more. The fading glow reveals a jet, relativistic, needle-thin, lighting up space in X-rays and radio. Beat. Neutrinos whisper. Gamma rays flicker. Beat. A multi-messenger postcard from the universe's heavy element foundry. Not every heavy atom comes from mergers. Some may spark in rare supernovae, but neutron star collisions are the champions we can see and weigh. Beat. LIGO, Virgo, Kagra are listening for the next one now. So, your favorite necklace? It's literally stardust, born in a cataclysm billions of years ago. Beat. You're wearing the ashes of ancient stars. Watch the gold drift. Soft whoosh. It returns to the nebula, to clouds, to worlds yet to come. Beat. In the end, the universe keeps nothing. It just passes the light along. Soft whoosh, gold particles dissolve into a star field. But how often do these mergers happen? Astronomers estimate a few per 100,000 years per galaxy, enough to seed the cosmos over time. Many occur in tiny ancient galaxies, others in star-forming spirals like ours. Beat. We trace their ashes in old stars, stellar archaeology, seeing europium and strontium born in our process fire. Meteorites carry the same isotopic fingerprints, ground truth from the early solar system. And colonovae likely power many short gamma-ray bursts, brief flashes from distant galaxies. Beat. Over billions of years, these explosions enrich gas clouds, building planets with veins of ore. Your body even holds a trace, atoms of heavy elements forged in ancient mergers. Next time gold glints, imagine two city cores colliding, writing jewelry into the periodic table. That's cosmic alchemy you can hold. Soft whoosh. We're ready for the next alert. Detectors ping, telescopes pivot, spectra bloom with fresh, heavy atoms. When it happens, we'll watch creation in real time. The Milky Way holds an estimated 300 to 500 billion stars. Compare that to roughly 110 billion humans who've ever lived on Earth. For every person who's ever existed, there are several stars. each with its own planets, its own story, its own mysteries. Trivia: counting one star per second would take over 9,000 years. And that's just the Milky Way. There are trillions of galaxies in the observable universe. Little known fact, if even 1% of Milky Way stars host a life-bearing planet, that's billions of potential civilizations. The numbers are humbling. Picture unknown skies, clouds tinted by alien suns, oceans tugged by two moons, forests breathing chemistries we've yet to name. Somewhere, maps are being drawn, stories are being told, questions are being asked back at the stars. So the next time you look up at the night, remember, stars outnumber us all. Each one a reminder of how vast and mysterious our universe is. Look closely. The universe keeps the greatest crowds, quiet and shining. Roll the clock backward. Before cities, before firelight, the Milky Way was our first cathedral, an arch of cold flame carrying a continent of suns. Roll the clock forward. Those same suns keep burning. Long after today's names fade, long after our languages change. Time is the slow river that stars learn to swim. Here's another measure. Imagine a beach of fine sand stretching for miles. A handful is a town of stars. The shore is a galaxy. The ocean beyond is the cosmos. In that crowd, some stars are infants wrapped in nebulae. Some are elders cooling toward embers. Some are twins locked in a dance. Some carry rings. Some carry winds. Some carry storms. Some carry auroras. Some carry the seeds of worlds. Zoom out. The Milky Way is one glow in a small neighborhood, the local group. Itself, a thread in a web so large, we draw it with supercomputers. From here, the great question ripples outward. How many eyes are looking back? Trivia: if we could visit a new star system every day, we'd need 1,000,000 human lifetimes to see a tiny fraction of our galaxy. And our instruments are just beginning. We measure tiny starlight wobbles, watch planets transit like dust motes crossing a lamp, sniff atmospheres for water, oxygen, methane, faint signatures of chemistry and chance. Little known fact, red dwarfs, the dimmest and most common stars, may host more rocky worlds than all sun-like stars combined. Multiply possibilities by time. Billions of years, billions of suns. Probability has room to work. Imagine a shoreline under a crimson star. Two suns set, shadows braid, bioluminescent forests breathe out color. Somewhere, city lights trace rivers like veins. Or maybe it's just fireflies and the patience of night. We are one census line in a galaxy of multitudes. Our questions are small, but they're also infinite. Here's a different comparison. If you gave each star a single heartbeat, the Milky Way would sound like rain, a storm of quiet pulses filling the dark. And still, most of those stars will never know we were here. That's the gift. Meaning isn't imposed by crowds, it's discovered by looking up. We count because we care. We care because we're made of this place. Hydrogen kindled into thought dust learning to speak. So, count with me. One star for every ancestor who lit a fire. One star for every story told in winter. One star for every name we can't remember, and every life we never knew. And then keep counting. Past us, past now, until the numbers become a feeling. There are more stars in the Milky Way than humans who've ever lived. That's not a statistic. It's a map of humility. When the night clears and the ark returns, let it remind you, we belong to a countless sky. When you think of rings, you probably picture gas giants like Saturn, but small bodies can surprise us. Meet Chariklo, a tiny world 250 kilometers across with two delicate icy rings. And then there's Ida, an asteroid with its own moon, Dactyl. Even the underdogs can have entourages. Chariklo's rings were discovered in 2013 during a stellar occultation. A blink in a distant star's light revealed two narrow rings. Ida's moon Dactyl? Spotted by the Galileo spacecraft in 1993, the first confirmed asteroid moon. Chariklo's rings, 7 kilometers wide, 3 kilometers wide, separated by a narrow gap. Haumea, a dwarf planet, also shows a thin ring. Over 200 asteroids now have moons, some binaries, some trinaries. Perhaps faint, dusty rings we haven't detected yet. Mini-planetary systems showing gravity's rules at tiny scales. Dozens show binary light curves revealing hidden partners. How do they form? Collisions kick up debris into rings. Captures trap tiny companions. Rubble pile gravity choreographs orbits. Light pushes dust outward. Gravity draws rocks inward. Over time, structure emerges. Occultations let us read the unseen. A star dims, brightens, dims again, drawing ring maps in milliseconds. Spacecraft flybys freeze moons in a single frame. Chariklo and Ida remind us the solar system is full of surprises. Even small rocks can carry rings and moons dancing in the dark. Look closely. Complexity isn't reserved for giants. It appears wherever gravity has time. From grand planets to pebble worlds, rings and moons scale down beautifully. Tiny systems, same physics. Asteroid rings fading into a starry field. Beyond Chariklo and Ida, more small bodies surprise us. Haumea shows a ring. Hints surround Chiron. And in 2023, Quaoar stunned astronomers with a ring far beyond the classic Roche limit. That ring around Quaoar orbits so far out that icy particles should clump. Yet they don't. Collisions and gentle resonances can keep grains apart, delaying moon-making. Beat. How do we detect such tiny structures? Stellar occultations are the trick. A background star blinks, brightens, then blinks again, drawing a ring map in milliseconds. Other tools help too. Light curve dips reveal moons. Radar pings sculpt shapes. Adaptive optics freeze fast specks beside brighter rocks. Beat. Formation basics. Collisions kick up debris into a thin sheet. Gravity sorts fragments into rings. Clumps become moonlets. Mini systems echoing giant planets. Spin can help. The Yorp effect, sunlight torque, spins rubble piles faster, lofting material toward an equatorial ridge. Some escapes into a ring. Beat. Where rings and moons survive depends on the Hill sphere, the tiny bubble where a small body's gravity wins against the sun's tides. Inside it, companions can persist. Ida and Dactyl show the pattern. A moonlet circling a potato-shaped world, orbits tidally nudged into stability over eons. Beat. Recent headline, DART's 2022 impact on Dimorphos proved we can tweak an asteroid moon's orbit. Even tiny systems answer to gentle pushes. Statistics grow fast. Hundreds of binaries, a handful of ringed small bodies, many more suspects awaiting the right alignment and clear skies. Beat. What keeps rings narrow? Shepherd moonlets do. Tiny Prometheus-style guardians at small scales, herding particles into lanes with subtle gravity taps. Over time, grains frost, clump, and sometimes merge. Rings fade into moons, or moons grind back into rings after new impacts. A cycle of building and unbuilding. Beat. Why it matters. These miniature laboratories test orbital mechanics, collisions, and the birth of satellites. Physics we scale up to planets and giant rings. So next time you picture asteroids, add rings and moons to the image. Tiny worlds with company, dancing by faint light. Look closely. Complexity lives small. The next time you watch a meteor shower, watch the colors. Those streaks aren't just white, they burn in chemical signatures. Magnesium flares blue-white, calcium pushes violet, sodium blazes orange, iron blends yellow-white, nickel and copper add a greenish tint, mixes of minerals paint mixed spectra. Meteoroids hit the atmosphere at up to 70 kilometers per second. Air slams into a shock front, heating to thousands of degrees. Surface minerals ablate. Atoms ionize and a glowing plasma sheath forms. As those excited atoms calm, they emit light at specific wavelengths, their emission lines: sodium's bright orange D lines, magnesium's blue-white triplet, calcium's violet lines, iron's dense yellow-white blend. It's spectroscopy, written across the sky. Most meteors are sand-sized, quick, colorful flashes. Bigger ones can become bolides, fireballs that fragment and sometimes explode. 2013. Chelyabinsk bolide flashes across morning skies. A multicolored burst is followed by a powerful shockwave, broken windows and damaged buildings in the aftermath. Safety first. Never hunt fragments until authorities say it's safe. So, when a meteor shower sweeps by, you're watching real-time cosmic chemistry. Elements revealing themselves in color, painting the night with clues to their origins. Look closely. The universe leaves its spectrum in every streak. Colors also come from our air. Oxygen glows green, nitrogen reddens the tail. Beat. Fast meteors ionize atoms. As they relax, they paint precise wavelengths, nature's barcode. Sometimes a persistent train lingers, twisting smoke lit by chemistry and winds. Beat. Fireballs fragment. Each piece flashes a different mix: orange sodium, blue-white magnesium. Showers differ by parent bodies. Comets and asteroids seed distinct mineral recipes. Beat. Result. Some showers skew greenish, others more yellow-white. Chemistry in the sky. Viewing tips. Find dark skies. Face away from city glow and ditch phones. Beat. Best time is after midnight. Earth's leading face plows into more meteoroids. Let eyes adapt 20 minutes. Use a red flashlight. Dress warm. Get comfy. Beat. Photography. Wide lens. High ISO. 10 to 20s exposures. Continuous shots toward the radiant. Try a simple diffraction grating. Yes, amateurs can capture meteor spectra at home. Beat. Find the radiant. Extend meteor paths backward. That starry point names the shower. At evening start, watch for earth grazers. Slow, horizon-hugging, long-colored streaks. Beat. Most meteors vaporize. A few drop meteorites, never trespass, and follow local guidance. Radio meteors. Ionized trails reflect radio. Hear pings even through clouds. Beat. Next shower. Watch the palette. Greens, oranges, blues, cosmic elements signing the night. Then breathe. Every streak is a tiny world ending in light. Beat. From minerals to colors to spectra, meteors turn physics into fireworks. Look closely. The universe signs its name in light, element by element. Whoosh! Wide shot of the solar system. Two pale giants glow at the edge. Beat. Uranus. Neptune. Billions of years ago, the outer solar system might have been a cosmic dance floor. Advanced models suggest Uranus and Neptune could have swapped orbits during the solar system's chaotic youth. Soft whoosh. Watch their paths cross. A graceful exchange. Beat. The kind of move that can leave lasting scars, like Uranus tilted on its side. Its rings and moons circling like a tipped-over top. Soft pulse. Where does this come from? The Nice model. Named for Nice, France. Giant planets didn't form where we see them now. They migrated, pushed and pulled by a vast disk of icy planetesimals. Picture it, a swarm of countless frozen worlds. The giants plow through this debris sea. Every close pass is a gravitational nudge. Tiny pushes, repeated millions of times. Beat. Jupiter tends to move slightly inward. Saturn adjusts. Uranus and Neptune are shoved outward, step by step. At some point, an instability. Whoosh! Jupiter and Saturn cross a key resonance, like two metronomes syncing, then slipping out of step. That resonance crossing can ripple outward, scattering Uranus and Neptune through the disk. In some simulations, they trade places, Neptune surging past Uranus into a wider, colder orbit. Uranus dropping inward for a time before settling farther out again. A swap, then a settle. The outer architecture rearranged. Neptune likely formed closer in. denser and more compact than Uranus. On screen. Formed closer in, migrated outward. It helps explain the Kuiper Belt's sculpted edges. Families of objects locked into rhythms with Neptune. Resonances. A spike in impacts called the late heavy bombardment. Note, the timing and intensity are still debated. Now, Uranus, the oddball. A world rolled 98 degrees onto its side. On screen, 98-degree tilt. One leading explanation, a colossal collision during that chaotic era. A planetary embryo the size of Earth or larger sideswipes Uranus. Slow, resonant impact sound, knocking it sideways. Rings and moons realign around the new equator. Seasons become extreme. Decades of daylight, then darkness at the poles. Beat. Combine that impact with migration chaos, and you get a tilted ice giant in a newly shuffled lane. Listen to the outer orchestra. As Neptune moved outward, it didn't just drift, it conducted. It shepherded distant worlds into stable steps. On screen, resonance. Pluto's 3-2 resonance means for every 3 laps Neptune makes, Pluto makes 2. It's a gravitational waltz that keeps close encounters at bay. Many Kuiper Belt objects share these locked timings, evidence of Neptune's outward sweep. Whoosh. Pull back to see the whole migration sequence. Early compact giant planet lineup, a thick debris disk beyond, resonance crossing, instability, scattering. Uranus and Neptune trade lanes in some runs. The disk is depleted, like a snowplow clearing the street. The giants settle into today's pattern. On screen, present-day layout. Why does a swap matter? Because it shows that even planets are not fixed. Their positions are chapters, not titles. Migrations set delivery routes for comets and water. They sculpt belts and gaps. Quick clarity. Not every simulation shows a clean swap. But many credible runs reproduce today's solar system best when Uranus and Neptune at least cross orbits. The physics is robust, the details are probabilistic. Zoom back to Uranus. Tilted rings, sideways magnetosphere, moons tracing circular paths around a planet rolling along its orbital plane. Summers that last 21 Earth years at the poles. Winters just as long. Zoom to Neptune. Deep blue, winds racing the fastest in the solar system. A planet that likely started warmer and nearer, then moved outward, bringing order to the Kuiper Belt as it went. Pluto and company keeping time behind it. On screen. Nice model. On screen. Resonance. On screen. 98-degree tilt. Soft whoosh. Imagine being there, if there could be safe. The sky filled with slow-motion catastrophes you could never feel in real time. Planets drifting miles per hour, not miles per second. We look at the night and see stability, but the record says motion, migration, exchange, a long dance that ends in a pose. Return to the wide solar system vista. Lines settle. Uranus and Neptune glint in their current places. The choreography complete, for now. The dance of Uranus and Neptune shows how dynamic our solar system once was. Even planets can change places, rewriting their cosmic story. Gentle whoosh. Look closely. Even giants can change steps. Soft whoosh. In 1054, skywatchers saw a guest star so bright it shone in daylight for weeks. A supernova, the explosive death of a massive star. Today, we see its ghost as the Crab Nebula filaments of glowing gas racing outward at over 1,000 kilometers per second. Beat. Across centuries, the ember keeps expanding, a time-lapse written in light. Records came from everywhere. Chinese court astronomers, Japanese chronicles, Middle Eastern scholars, notes of a star that appeared, then slowly faded. Even in North America, some think a Chaco Canyon petroglyph captures the Site crescent moon, bright star nearby, an echo in stone. Beat. Distance check. The nebula lies roughly 6,500 light-years away in Taurus. Its light first reached Earth around 1054. At its heart spins a pulsar, a city-sized neutron star, turning 30 times each second, sweeping beams like a cosmic lighthouse. Beat. X-rays, gamma rays, radio waves. The pulsar winds inflate a glowing bubble, powering the crab's eerie blue haze. Under high magnification, threads twist like tangled silk filaments, rich in oxygen, sulfur, hydrogen, lit by shock waves. Beat. Watch carefully, and you can measure motion in mere years. Arcs drifting outward, proof of an everlasting blast. How bright was the original? For weeks it rivaled Venus, visible at noon, a beacon that rewrote night. Beat. Supernovas forge elements. Calcium in our bones, iron in our blood, seeded by explosions like this one. Timeline. Massive star lives, fast core collapses, shock rebounds, star unravels, a neutron star remains, the nebula blooms. Beat. Little known fact. The crab pulses so steadily, its timing helped calibrate early X-ray telescopes and even test relativity effects. Through Hubble JWST, we map waves, measure speeds, and read chemistry. Astronomy as forensic science. Beat. Stand beneath winter skies. Find Taurus, then M1 in binoculars. Faint oval haze, a whisper from 1054. Because the Crab Nebula is a time capsule, we witness a millennium-old event still unfolding tonight. Beat. It's proof the universe's past is alive in the present. Echoes written in light. Look closely. The dead star's heartbeat still glows. Fade. The nebula dissolves into a quiet, starry expanse. How to see it yourself. Find Taurus near Zeta Tauri. In binoculars, look for a faint oval glow labeled M1. A small telescope shows texture. An O3 filter boosts contrast by highlighting oxygen's blue-green glow. In photographs, combine wavelengths. H-alpha red for hydrogen, teal O3 for oxygen, and S2 for sulfur, each tracing different shock fronts. Watch time pass. Across a decade, filaments crawl outward. Astronomers measure proper motion to clock the blast's age. At the heart, the pulsar powers a wind nebula. Wisps ripple like smoke as magnetic fields channel particles near light speed. Radio maps reveal cold electrons. X-rays expose the hottest knots. Infrared traces dust forged in the blast. Future planets in the making. Light echoes can still appear. Supernova light bouncing off distant dust, replaying the explosion centuries later. Observing tips, dark skies, steady mount, long exposures. Try stacking images. Let the nebula's faint glow build with time. So when you spot M1, remember, you're seeing 1,000-year-old shockwave still unfolding. Look closely. The universe keeps its memories in motion. Soft whoosh. Wide, star-speckled vista. In 2017, astronomers spotted something bizarre. A cigar-shaped object tumbling through space at roughly 315,000 kilometers per hour. On-screen label, 2017. They named it Oumuamua, Hawaiian for scout. It wasn't from our sun. It came from another star system, the first interstellar visitor we've ever confirmed. We caught it with the Pan-STARRS telescope in Hawaii. Discovery alerts ping telescope domes open nighttime pan over Pan-STARRS, lower third, Pan-STARRS, Hawaii. Its speed and trajectory ruled out a native comet or asteroid. It never settled into an orbit. It simply passed through. Side by side, a bound ellipse versus Oumuamua's open escape path. It dove in from above the ecliptic, whipped around the sun, and climbed back out on a one-time visit. Trivia. Oumuamua showed a gentle non-gravitational acceleration, too small for a rocket, but puzzling. At first, we saw no obvious comet tail. Later, modeling suggests invisible outgassing, perhaps hydrogen or supervolatile ices, could have provided a faint push without a visible plume. Its light curve swung wildly as it spun, up to 10-to-1. That hinted at an extreme shape. Was it a stretched spindle or a thin pancake-like shard? Either way, not your average rock. Little known fact. Some proposed an exotic idea, a light sailing object, an artificial sheet propelled by sunlight. Speculation. Most scientists favor a natural origin, but the mystery sparked debate. Natural scenarios abound. A crust fractured from a dying planet, a nitrogen ice shard chipped from a Pluto-like world, or a carbon-rich body baked and reshaped by eons between stars. What we know for sure, it came from the deep between stars, looped past our sun once, and slipped back into the dark, never to return. Since then, we've found another interstellar visitor, 2I Borisov, a more familiar comet with a clear tail. Together, they hint the galaxy may be teeming with wanderers. We're getting ready for the next one. Surveys like the Vera C. Rubin Observatory's LSST will scan the sky deeper and faster, giving us earlier warnings, and maybe a chance to send a probe. Imagine launching a rapid interceptor, solar electric engines humming, plotting a sprint to a target escaping the solar system. Close encounter, mapping the surface with LiDAR, sniffing gases with spectrometers, reading isotopes that tell where it formed, cold outskirts of a distant star, or somewhere stranger. We could learn how interstellar travel weathers rock and ice, how radiation darkens, how heat fractures, how sunlight gently sails the thinnest shards. Oumuamua left as quickly as it came, but it reminds us the space between stars isn't empty. It's a highway of drifters. Somewhere out there, the next scout is already on its way. Discovery, October 19, 2017. Pan-STARRS flagged a fast mover in nightly images over Hawaii. Automated scans stitched a tracklet. Humans double-checked the outlier. Follow-ups quickly showed something wild. Its path wasn't a bound ellipse. The orbit was hyperbolic, meaning it came from interstellar space. Numbers: eccentricity about 1.2. Perihelion, September 9, 2017. Closest to Earth, October 14, roughly 24 million kilometers. It started as A/2017 U1. After confirmation, the IAU created a new class, 1I for first interstellar, name Oumuamua, Scout. Photometry told the shape story. A 10-to-1 brightness swing suggested an extreme body, rotating and likely tumbling with a period of hours. Then came the subtle push. Non-gravitational acceleration. The best natural explanation, tiny outgassing from super volatile ices, too faint to show a tail. Teams worldwide chased it, VLT, Hubble, and more. Spitzer didn't detect heat, capping the size and hinting at a highly reflective surface. By November, it was already dimming fast, outbound toward Pegasus. With each night, fewer photons, more questions. Takeaway: new surveys must react instantly. Catch the next interstellar scout earlier, and we can read its chemistry in detail. Maybe even send a probe. To our eyes, the moon is a silver-gray orb, but it's hiding a secret. It's more colorful than you think. Beat. Advanced imaging reveals subtle blues, yellows, and sandy browns, clues to its minerals. Visual: LRO false color composite. Seas, shift blue-teal, visual. Highlands tan, TiO2, titanium. Bluer FeO, iron. Redder brown. Those hues trace ancient lava plains, volcanic glass, and titanium-rich soils. Natural view, enhanced view. The colors are faint because lunar soil is weathered by micrometeorites and solar radiation. Space weathering that darkens and mutes pigments. Beat. Clementine Chandrayaan. LRO context imagery. Spacecraft like Clementine and Chandrayaan-1 mapped composition from orbit. Titanium-rich blue mare basalts and iron-rich red terrains. Tie-rich mare, Mare tranquillitatis, pop-up. Phi-rich basalt, Mare imbrium, pop-up. Mare tranquillitatis skews blue thanks to titanium-bearing ilmenite. Mare imbrium trends browner with higher iron. Visual: rotating lunar globe with pins dropping on major Maria. The moon's Maria, dark flat plains, are flood basalts from eruptions billions of years ago. Glassy beads from fire fountain eruptions sparkle. Angular rock fragments, breccias, tumble in microshadow. Some regions hold volcanic glass beads, Tiny spheres that once rained from lava fountains, sparkling in colors our eyes can't easily see at night. Beat. 415 nm 750 nm 1000 nm filter stack. Ratios blend into a false color composite. By combining light through different filters, scientists amplify subtle differences our eyes miss. Fresh, bluer ejecta rays from Tycho lace across older terrain. Nearby regions shift toward redder brown with age. Fresh material is bluer. Ancient, sun-baked soil shifts toward warmer tones. Tagged basalts, bright anorthosite, vivid orange soil, Apollo 17. Apollo samples match the maps. Iron-rich basalts, pale anorthosite highlands, and even orange volcanic soil, glass formed in explosive eruptions. Sunlit rims glow with faint color. Interiors remain ink black. Trivia. Clementine and Chandrayaan-1 helped chart titanium-rich blue and iron-rich red regions. Trivia. These global maps let us track titanium and iron from orbit, painting a chemical portrait of our neighbor. Little-known fact. The moon's glass beads encode eruption chemistry. Under lab lights, their colors sing. Natural moon versus modest true color processing from backyard images. Try slight saturation, IRUV cut filter. You can glimpse this at home. Shoot the moon and nudge saturation. The rainbow is faint, but it's there. Beat. Mare tranquillitatis, T-rich blue. Mare serenitatis mare imbrium. Oceanus procellarum. Impact lava time and sunlight turning geology into color. Grayscale slowly fades in. Then color creeps back along basins and rays, breathing like a tide. The moon's hidden rainbow reminds us, even our closest neighbor has secrets, waiting for the right tools and a careful look. Visual outro. The color-rich moon dissolves into a soft, colorful cosmic field, ready for the end sting. At night, stars look like white pinpricks. But that's an illusion. They come in a dazzling array of colors. Red, orange, yellow, white, blue, each hue a clue to temperature. Cool stars glow red. The hottest burn blue. Think of a cosmic thermometer. Red, about 2,500 to 3,500 Kelvin orange. Around 3,500 to 5,000 Kelvin yellow. 5,000 to 6,000 Kelvin white. Near 6,000 to 7,500 Kelvin blue-white to blue. 7,500 up past 40,000 Kelvin and our sun, technically green-white in its spectrum. But Earth's atmosphere and our eyes make it look yellow. You can see this with your eyes under dark skies. Aim for a moonless night. Let your vision adapt. Arcturus glows orange. Vega shines blue-white. Rigel is icy blue. Antares is deep orange-red. With binoculars, the colors pop even more. Sirius, our brightest star, blazes blue-white. Betelgeuse is a red supergiant, cooler but huge and nearing a future supernova. Physics paints the palette. Hotter stars peak bluer. Cooler stars peak redder. Their atmospheres leave spectral lines, dark notches and bright fingerprints. So when you scan a constellation, notice mixed hues side by side, embers and ice sharing the same sky. Little known fact, your eyes can catch these colors if the sky is dark enough. Try averted vision. Keep lights off your screen. Give yourself 20 minutes to adapt. A steady view through binoculars or a small scope makes colors richer. The next time you stargaze, look for the colors. The sky isn't just white. It's a cosmic palette painted by stellar temperatures. Color classes: O, B, A, F, G, K, M, blue to red. Mnemonic: O, be a fine girl, guy, kiss me, beat. Most stars are cool red dwarfs, tiny, numerous, long-lived. Blue giants are rare but brilliant, short, intense lives. Astronomers use color index, B-V, to quantify hue. Lower BV, bluer, hotter. Higher BV, redder, cooler. Interstellar dust reddens light. Distant stars look warmer. Atmosphere matters. Low stars look orange through thicker air. High overhead, colors are truer. Less scattering, cleaner spectra. Your eyes switch modes, scotopic to photopic, changing color sensitivity. Tip: let eyes adapt 20 minutes, avoid screens, use red light. Binoculars concentrate light, colors pop on bright stars. Double stars show contrasts, Albireo pairs gold and blue. Open clusters sparkle with mixed hues, Pleiades, Hyades, Beehive. Long exposures exaggerate color, cameras see what eyes barely catch. Spectral lines encode chemistry, hydrogen, helium, metals, each imprinting. Color foretells fate. Blue giants die fast. Red dwarfs outlive galaxies. Seasonal tour: winter, Rigel blue. Betelgeuse red in Orion. Spring, Arcturus orange. Summer, Vega blue-white. Autumn, Fomalhaut pale. Twinkling distorts colors. Steady nights reveal truer tones. So remember, most stars aren't white at all. They're temperature made visible. Look closely. The night glows with physics and color. Diamonds aren't just Earth's gemstones. They're a cosmic treasure. Inside Uranus-Neptune, crushing pressure, crackling lightning may forge diamond rain, falling through their icy interiors. In storms rich with methane, carbon chains snap. Carbon condenses into tiny crystals. Seeds, they grow as they plunge, layer by layer, toward deeper, hotter seas. Picture hailstones, but made of diamond. Billions of glittering shards cascading in the dark, each one heavier, purer, as gravity pulls them down. Trivia: a white dwarf nicknamed Lucy, officially BPM 37093, sits about 50 light-years away. That stellar gem may be 100,000 times heavier than all Earth's diamond, reserves a lighthouse of crystallized matter, still ringing with starquakes astronomers can hear. Back home in the lab, we've tried the recipe. Laser shocks anvils squeeze methane to millions of atmospheres, out pop nano-diamonds. Models suggest crystals could collect into diamond bergs, floating in dense liquid layers deep inside the ice giants, drifting like icebergs in a midnight ocean. Deeper still, temperatures soar. Bergs melt, sink, refreeze, a slow glitter cycle powered by pressure and time. Future probes could chase the sparkle, sniff carbon measure, lightning listen for the soft ping of crystals forming in the dark. From raining gems to stellar diamonds, the universe proves that beauty and wonder are everywhere, even in the coldest corners of space. Look closely. The night is full of hidden fire, and sometimes it falls as diamonds. Little-known fact: meteorites carry nanodiamonds, cosmic crystals born in ancient explosions. In chondrites, some grains are only nanometers across, tiny but unmistakable. White dwarfs crystallize as they cool, carbon and oxygen locking into a vast lattice deep within. Astronomers read starquakes, asteroseismology, to weigh those crystal hearts. Candidate diamond planet, PSR J17191438b, ultra-dense carbon, likely orbiting a pulsar. Another suspect, 55 Cancri E, possibly carbon-rich. Details debated as data improves. Labs have made diamond rain with laser shocks, recreating ice giant pressures for microseconds. Compressed methane breaks and reforms. Carbon seeds snap into nanodiamonds. Deep inside Uranus and Neptune, diamonds may dissolve into hot, conductive fluids. Some models even suggest layered diamond oceans. Still speculative but testable. How to test it? An Uranus orbiter and probe, sampling gases while a descent probe measures depth profiles. Targets: carbon species, helium, lightning radio bursts, and gravity waves written into rings. Conductivity and density shifts with depth could reveal where crystals appear and melt. Beyond our system, carbon-rich super-Earths might hide deep diamond mantles under scorching skies. But many worlds are oxygen-rich. Silicates dominate, turning carbon into rock, not gems. Takeaway: diamonds may be common. Their fate depends on chemistry, pressure, and time. Look closely. The darkest planets can glitter within. Could we mine them? Not really. Depth, pressure, and distance make it fantasy for now. On white dwarfs, Crystal lattices can span thousands of kilometers. Stellar-scale gemstones. Starquakes ring like gongs. Timing those notes maps the depth of crystallization. Upcoming surveys will time pulsations with higher precision, clearer pictures of frozen cores. Nickname Lucy nods to a song. The cosmos loves a good lyric for its diamonds. Back to ice giants. Storms and lightning crack methane, stitching and breaking carbon chains. Crystals fall through ammonia water layers, warming as they descend into metallic seas. They may melt, sink, and refreeze, transporting heat like glittering raindrops in a loop. The story stands. Beauty is everywhere, even when it falls as diamonds. From raining diamonds to an infernal jewel. Meet Venus, Earth's evil twin wrapped in light. Hiding a furnace, Venus spins so slowly. One sidereal day takes 243 Earth days. It loops the sun in just 225 days, a day longer than a year. On Venus, clocks and calendars part ways, and it spins backward. Most planets turn counterclockwise. Venus rolls clockwise. So the sun appears to rise in the west and set in the east. Stand on the surface, if you could. You'd wait months for sunset. The sky would glow a dim orange, the sun a smeared ember behind permanent clouds. Because Venus rotates backward while it orbits forward, the solar day, time from noon to noon, is about 117 Earth days. Still months long, but only half the spin length. On Venus, day and night crawl. Those clouds are deadly, a cloak of sulfuric acid droplets. They reflect sunlight. Venus is our brightest planet. But below that reflective armor, heat is trapped. Atmosphere, thick carbon dioxide, with a dash of nitrogen. Pressure crushes at 92 times Earth's surface pressure, like standing a kilometer under the ocean. Temperatures average 460 degrees Celsius, hot enough to melt lead, melt solder, and kill most spacecraft electronics. Wind near the ground creeps at walking speed, but the air is so dense it behaves like syrup, sanding rocks over eons. Higher up, the atmosphere roars. At cloud tops, winds race around the planet in about 4 Earth days, a super-rotating jet stream lapping the world while the surface barely turns. The clouds flash with lightning. They produce ultraviolet dark streaks of mysterious chemistry. Spacecraft keep chasing those streaks. We've seen the surface only through radio eyes and brief, heroic landings. 1970s-80s Soviet Venera probes parachuted into the oven. They touched down. They survived for minutes, 23, 50, 127. Then heat and pressure silenced them. The images they sent, flattened, angular rocks, a horizon sagging in hot haze, the color of rust in perpetual dusk. NASA's Magellan mapped Venus with radar. It revealed volcanoes, lava plains, pancake domes. Crumpled terrains called tesserae rise like continents. Fresh clues suggest Venus might still be geologically alive. A volcanic vent in Magellan data appears to have changed shape. Venus Express saw thermal hotspots. Akatsuki tracked shifting cloud patterns. The planet breathes heat. Why does Venus spin slowly and backward? One idea, a colossal impact early on. Another, the sun's pull and atmospheric tides. Over millions of years, torques could break and flip rotation. The result is a world where clockwork runs strange. Living there? Not with current tech. Electronics fail in hours. Lubricants boil. Solder droops. Engineers test silicon carbide electronics that can function for weeks. Balloons may be our best bet. At about 55 kilometers altitude, the air is benign. Pressure like Earth's sea level. Temperatures like a hot day in the desert. A floating lab could ride the winds around the planet, peering down through gaps in the clouds, sniffing atmospheric chemistry, listening for thunder. Radar is our flashlight. Thick clouds block visible light. Radio waves from orbiters can map the ground, track tiny spins in the planet's rotation, sense how the atmosphere tugs on the crust. Recent radar shows Venus's length of day drifts by minutes. The atmosphere speeds up and slows down. Weather literally pushes the planet's rotation. We'll be back soon. Da Vinci will plunge through the atmosphere, tasting gases, measuring pressure, imaging ancient tesserae. Veritas will remap the surface in exquisite detail, hunting for fresh lava, hunting for quakes. ESA's Envision will probe the crust and mantle. Venus may have begun as a near twin of Earth. Oceans, clouds, rain, then tipping into a runaway greenhouse. By reading its rocks and air, we read a cautionary tale. We learn how to spot Earth-size worlds that could be Venus's, not Earth's. From Earth, Venus shows phases like the moon, crescent, full. It has crossed the sun's face in rare transits. It looks serene in a telescope. It's anything but. A planet where a day outlasts a year, where the sun sets in the west, and where the air itself weighs like an ocean. Venus reminds us nearby can still be alien. The universe loves to rewrite the rules we think we know. From comet dust in our hair to diamonds raining on distant worlds, from stars we could touch to planets that swap places. The universe is a place of endless wonder. Every gold ring, every shooting star, every glimpse of the night sky connects us to a story billions of years in the making. Astronomy doesn't just show us the cosmos, it reminds us that we're not separate from it. We are the universe, made conscious, looking back at itself. Beat. Which of these discoveries blew your mind the most? Drop a comment below and let's keep exploring the cosmos together. Don't forget to like, subscribe, and hit that bell for more cosmic wonders.